Good morning, class 12. Let's start. Today we are going to discuss the physical properties of alkyl halides. First one, physical state. Some of the lower haloalkanes are gases. All other halides up to C18 are sweet-smelling oily liquids. Higher members are solids. Alkyl halides are colorless when pure. However, bromides and iodides develop color when exposed to light. Melting and boiling points. Carbon-halogen bond in case of alkyl halides is polar in nature due to the electronegativity difference between carbon and halogen. Due to the polar nature, the boiling points of alkyl halides are much higher than that of the corresponding alkenes. This is because of strong dipole interaction between the molecules of the alkyl halides. Now, the boiling points of different types of alkyl halides are in the order this is due to the polarizability of the iodides. Okay, iodides due to large size possess greater polarizability and due to which they have greater boiling point. I mean, the dipole interactions are stronger, that increases the boiling points of the halides. Okay, the boiling points of chlorinated derivatives of methane increases with increase in the number of chlorine atoms because of increase in the van der Waals forces. For same halogen, boiling points increases with increase in molecular weights. If I consider this, as I am moving from left to right, the size of the alkyl group increases, so the molecular weight increases, van der Waals interaction increases, boiling point increases. This is the order of the boiling point. Okay, for same type of halogen atom. For isomeric alkyl halides, boiling point decreases with branching of the carbon chains. This is because with branching of carbon chains, there is decrease in the surface area, which decreases the van der Waals force of attraction. So, this is N-butyl chloride. Next, if I draw isobutyl chloride. Last one, tertiary butyl chloride. As I am moving from left to right, the branching increases, which decreases the van der Waals force of attraction, and so the boiling point decreases. Next point is dipole moment. Polar character and thus dipole moments decreases from chloro to iodo derivatives due to decrease in the electronegativity of the halogen. Fluorides, however, have lower dipole moment than chlorides. This is because of the smaller CF bond length, which outweighs the effect of greater electronegativity. Last one, solubility. In spite of their polar nature, haloalkanes are insoluble in water. It is due to their inability to form hydrogen bonds with water. In order for a molecule to dissolve in water, energy is required to overcome the attractive forces already existing between haloalkane molecules and to break the hydrogen bonds already existing between water molecules. On mixing haloalkane with water, less energy is released, which is not sufficient to overcome the existing attractive forces because the new attractive interactions are not so strong as the hydrogen bonds already existing between the water molecules, right? Due to which they are insoluble in water. Now we come to the reactivity or reactions of haloalkanes. Okay. Haloalkanes, they are highly reactive. In nature. Their reactivity is because of the presence of the polar carbon-halogen bonds. Order of polarity is what? Polarity order is this one. CF, then CCl, CBr. Okay, this is the order of polarity, and the order of reactivity is just the opposite. That means alkyl iodides are maximum reactive, okay, and alkyl fluorides are least reactive in nature due to their bond dissociation energy. Because alkyl iodides, they have minimum bond dissociation energy, so easily it can be broken and easily reaction occurs. Okay, here the main reactions, the main types of the reaction. First is nucleophilic substitution reaction. Under this, you have the examples and the mechanism of both SN1 and SN2. Then we come to elimination reaction. Here also we have the mechanism. Last one, we have reactions with metals. So, examples of nucleophilic substitution reaction. first one, substitution of halogen by hydroxyl group. This is formation of alcohols, or I can say this is hydrolysis of alkyl halides. So in this particular reaction, alkyl halides, if I take ethyl bromide treated with aqueous KOH or moist silver oxide. Moist silver oxide means this one. This is moist silver oxide. If the alkyl halides are treated with aqueous KOH or moist silver oxide, we will be getting what? Respective alcohols. So in this case, C2H5OH plus KBr. This is hydrolysis reaction. Okay, next, substitution. This was substitution of halide ion by the hydroxyl group. Okay, both are nucleophiles, right? Both Br negative is also nucleophile, OH negative is also a nucleophile, so they are getting just replaced. That side is known as nucleophilic substitution reaction. Next is substitution of halogen by cyano group, that is formation of alkyl cyanides. Whenever alkyl halides treated with potassium cyanide, I mean alcoholic solution of potassium cyanide, we get what? We get alkyl cyanide, or I can say alkyl nitriles. This is the side product. Okay, now when alkyl halides are treated with alcoholic solution of potassium cyanide, we get alkyl cyanide as the major product with small amount of alkyl isocyanides. Okay, because cyanide is an ambidentate ligand, so the attack can occur from both carbon and nitrogen end. Okay, next, if we treat alkyl halides with silver cyanide, alcoholic solution of silver cyanide, we get alkyl isocyanide as the major product. KBr is the side one, and we get small amount of alkyl cyanides. Here this one is the major product. So whenever alkyl halides are treated with ethanolic or alcoholic KCN, alkyl cyanides are obtained as the major product, while when they are treated with alcoholic AgCN, we get alkyl isocyanide as the major product. Now why? Because whenever we are using KCN, KCN is an ionic compound, so it dissociates to give K positive and Cn negative. So in this particular case, both carbon end and nitrogen end are free to attack the alkyl halide. Now since CC bond is more stronger than CN bond, therefore the attack occurs through the carbon end, and here cyanide is obtained as the major product. Okay, but when silver cyanide is taken, AgCN, it is a covalent compound, and this case only the nitrogen end is free. So the attack occurs through nitrogen end, and we get alkyl isocyanides as the major product. It is happening because of the ambidentate nature of the cyanide ion. Okay. Next, we move to substitution of halogen atom by alkoxy group, or I can say formation of ethers. This we spoke about formation of alcohols, then formation of alkyl cyanides, and then alkyl isocyanides. So formation of ether C2H5Br when treated with sodium ethoxide. So here this is my nucleophile and this is also my another nucleophile, right? So Br will be replaced by this OC2H5. This particular reaction is known as Williamson synthesis, and this is formation of ether. This is diethyl ether or ethoxyethane. Okay, this particular reaction can also be carried out in presence of silver oxide. If I take two molecules of ethyl bromide and silver oxide, I get diethyl ether C2H5 OC2H5 plus 2AgBr. Okay. Now next is formation of alkyl nitrites and nitroalkanes. So whenever alkyl halides are treated with sodium or potassium nitrate solution, then what do we get? Here also this NO2. NO2 is an ambidentate nucleophile. Okay, this particular part is an ambidentate nucleophile. So here the attack can occur via oxygen end or nitrogen end. KNO2 is an ionic compound. So here both nitrogen and oxygen ends are free. Now carbon-oxygen bonds are more stronger than carbon-nitrogen bonds. So in case of this particular reaction, we get alkyl nitrites as the major product. This one. This is CH3, CH2. This is alkyl nitrate, or I can say ethyl nitrite. Ethyl nitrate, carbon-oxygen bond is formed, and here the byproduct is your KBr. Okay. Next, if C2H5Br is treated with silver nitrite. Silver nitrite. Now silver nitrite is a covalent compound. Like KNO2 or NaNO2, they are ionic compounds. Silver nitrite, it's a covalent compound. So here only nitrogen end is free. Okay, oxygen end is not free. So since nitrogen end is the only free end, so the attack will be occurring via nitrogen, and we are going to get what? Nitroalkane. So here I am going to get NO2. C2H5NO2 plus AgBr. Okay. Last is ammonolysis of alkyl halides. Ammonolysis of alkyl halides. So in case of ammonolysis, what we have to do? We have to use alkyl halide. First step, ammonia. Ammonia has lone pair. It is attacking the carbon end. Br will move out. So what do we do? What do we get? CH. This is NH2, CH2 plus HBr. Because Br is moving out, 1 H we are getting from ammonia. So this is the thing. This lone pair of nitrogen is attacking the carbon. Which carbon? CH2 carbon. Because C2H5Br means what? CH3, CH2Br. It is attacking the CH2 carbon, not the CH3 carbon. Okay. Next step, what we are doing? Again, we are taking CH3, CH2Br. Plus this 1 degree amine is produced. So again the attack will be happening from the nitrogen lone pair, and NH C2H5. Okay, this is the major product. This is your 2 degree amine. And side product, what is the side product? Side product is your HBr. Next step, again we are taking CH3, CH2Br plus this 2 degree amine. What do we get? 3 degree amine. C2H5. Here also C2H5. This is 3 degree amine. Further, this part reacts with your ethyl bromide to form quaternary ammonium salt. Okay. This is 3 degree amine. Further reacts with alkyl halide to give you what? Quaternary ammonium salt. Quaternary means when nitrogen's valence is complete, it is positive charge. C2H5, and here also one C2H5. Positive. Okay. So that's it, class 12. Thank you.